Hi there, this is Tang from the University of Delaware. Today I will be presenting our paper entitled Are Data-Driven Explanations Robust Against Out-of-Distribution Data? To give you an overview, we comprehensively studied three research questions. First, are data-driven explanations robust against OD data? Our experiments suggested that data-driven explanations are unreliable under distributional shifts. Second, how to develop robust explanations. We propose an end-to-end model-agnostic learning framework, Distributionally Robust Explanations, DRE. The key idea is utilizing the interdistribution information to provide supervisory signals for the explanation learning. Third, can robust explanations benefit the model's generalization capability? Our experiments indicate that robust explanations significantly improve the model's prediction on OD data. As black box models increasingly power high-stake applications such as healthcare, criminal justice, finance, and self-driving cars, the absence of reliable explanations can lead to severe consequences. It can cause catastrophic outcomes in these high-stake applications and would violate the regulations. For example, the General Data Protection Regulation from the EU empowers individuals with the right to demand explanations of an AI system. The existing works on explainable machine learning can be categorized into two categories. First, intrinsic methods, whose explanations are inherent to the model architecture and training. However, many recent works show that there is a trade-off between interpretability and accuracy. Then practitioners tend to use the second category, post-hoc methods, which provide explanations for a pre-built model in a post-hoc manner while keeping high performance. However, they are not robust against distributional shifts and unreliable on OD data. To understand the OD challenge, we need to recap the underlying assumption of machine learning that the testing distribution is the same as the training. However, in real world, the assumption may not always hold. The testing distribution can shift due to spurious correlations, adversarial attacks, subpopulations, and naturally occurring variations. And the robustness of data-driven explanations against OD data remains a vital yet seldom investigated question. Again, here is the outline, the three research questions of this presentation. We explicitly design experiments to verify our first research question. Our observations are, qualitatively, even with correct prediction, the explanations would also highlight background pixels such as tree branches on OD data. And quantitatively, the explanation quality experiences a severe drop on OD data in terms of fidelity and scientific consistency. So the takeaway is that data-driven explanations are not robust against OD data. The explanations excessively rely on spurious correlations. How to develop robust explanations against OD data? In order to alleviate the reliance on spurious correlations, supervision of explanations are essential. They are typically derived from ground truth explanation annotations and one-to-one mapping between image transforms. However, there is a supervision gap in real-world scenarios. Obtaining ground truth explanation annotations are prohibitively expensive or even impossible. And there is no one-to-one mapping for naturally occurring distributional shifts in the wild. To address the limitations, we propose an end-to-end model-agnostic learning framework, Distributionally Robust Explanations, DRE. The key idea is inspired by self-supervised learning to fully utilize the interdistribution information to provide supervisory signals for the explanation learning. The core component of our method is the explanation consistency constraint. Specifically, we mix up samples from different distributions and their explanations correspondingly with the same parameters. Then we leverage the consistency between the mixed explanation and the explanation of the mixed sample as a constraint for optimization. Our method provides supervisory signals for the learning of explanations without human annotation, and achieve a simple but effective interdistributional transformation. We conduct extensive experiments to validate our third research question: can robust explanation benefit the model's generalization capability? For image classification tasks, we employ two OOD benchmark datasets, terra incognita in the wild camera trap images. Its distributions are identified by camera locations with different illumination, perspective, etc. And VLCS, its distributions are identified by different natural image subdatasets with different styles, backgrounds, etc. We use distributional consistency and explanation fidelity as the evaluation metrics. Our qualitative results indicate that our model alleviates the reliance on background pixels and ensure consistent explanations across distributions. Our quantitative results suggest that our explanations are more robust against distributional shifts and further improves the prediction accuracy on OOD data. So the takeaway is robust explanations significantly benefit the model's generalization capability by alleviating its reliance on spurious correlations. And our ablation study shows that our method strikes a good balance between optimization objectives. And the advanced explainability of our model can be generalized to other data-driven explanation methods, such as integrated gradients and shape. For the regression task on scientific tabular data, we use a large-scale spatial temporal dataset for urban land fraction prediction. Its distributions are identified by continental regions with different topographic, population, and historical urban fraction conditions. We introduced the scientific consistency metric, which measures the consistency between the explanations and ground truth domain knowledge. Our results show that robust explanations significantly improve the scientific consistency on OOD data. This finding would further catalyze scientific knowledge discovery by DRE, since explanations on unseen distributions can reveal unknown patterns arising from local data. The discrepancy between consistent and inconsistent explanations can be exploited for knowledge discovery. Our preliminary work on this topic won the Best Paper Award in MLPH workshop at NeurIPS 21. Thank you all for listening.